Welcome to our presentation on Recursive Contour-Saliency blending network for accurate salient object detection. I'm Yunyi Ke, and this work was done in Open8 Singapore AI Lab under the supervision of Takahiro Tsubono. Salient object detection aims to locate and extract the most attention-attractive object in a visual scene. It requires the predicted object with clean and sharp boundaries. In recent years, many algorithms have been developed for salient object detection tasks. Networks in the field can be categorized into two streams: contour-based methods and non-contour-based methods. Though various models have been proposed in the field, the edge quality of prediction still can be improved. And in this paper, we proposed a network to address this issue. Additionally, most of the networks in the field are heavy and over-parameterized. Big models can indeed improve performance, but it is hard to train and consumes a lot of computational resources during inferencing. Thus, we also want to develop a lightweight model without compromising the performance. Most of the salient object detection models in the field are essentially encoder-decoders. For encoder, pre-trained ResNet 50 or similar networks will be applied as the backbone for feature extraction, while for decoder, it can be divided into two categories. For contour-based models, a contour branch will be applied to fuse contour information with saliency branch. However, using this approach, the fusion is limited due to countable decoder stages, and fusion can only happen at the end of each stage. We call these drawbacks as limited fusion and late fusion. On the other hand, non-contour-based networks usually focus more on feature extraction module at the end of each decoder stage. By doing so, predictions from non-contour-based models usually have better structural properties, but lack of edge quality. To address above-mentioned issues and improve the performance, we proposed an early fusion mechanism where we designed a blending unit to exchange contour and saliency information, and we employ recursive CNN to unblock the restriction of limited fusion and late fusion. By doing so, contour and saliency information can now be exchanged as many times as possible and at a much earlier stage, which will greatly improve model's performance. Besides, we developed a stage-wise feature extraction module to help the network pick up the most useful information. The intermediate predictions shows the effectiveness of our approach, and as shown in the figure, our salient object predictions have a good edge quality. In addition to the network, we also developed two loss functions to boost model performance further. Firstly, we developed a dual confinement loss for better contour and saliency predictions. It is prevalent to using contour predictions as the weight map of BCE loss to confine saliency predictions. However, since contour and saliency information are highly correlated, similar to the contour loss, we also want to use saliency prediction to confine contour predictions. And thus, our dual confinement loss consists of losses from both contour and saliency. Secondly, we noticed that the network will counter two problems for most saliency predictions: confident but wrong predictions, and correct but unconfident predictions. Thus, we factor in confidence into our training and design the confidence loss. The confidence loss considers the saliency prediction and makes it into a heat map using the listed equation. Then we apply the map as a weight to BCE loss and also as a regularization term to optimize our model. The confidence loss turns out to be very effective as it can encourage the model to make more confident predictions into either foreground or background. We train our model using above-mentioned methods and evaluate on the benchmark datasets. For quantitative evaluation of our model, we obtained state-of-the-art results and outperforms most of the networks in the field. For qualitative evaluations, our model can effectively identify salient object and return it with good edge quality. This is due to the effectiveness of early fusion mechanism, stage-wise feature extraction module, and our design loss functions. Last but not least, as a favorable byproduct, our model can also generate contour predictions. Compared with other contour-based models in the field, our contour predictions are much cleaner and more complete, which further indicates the effectiveness of our algorithm. To sum up, our contributions of this work are fourfold. Firstly, we proposed a network with better salient object detection accuracy. Secondly, we proposed two new loss functions which can boost model performance. Thirdly, our model is lightweight with only 27.9 million parameters. And lastly, our model also returns cleaner and more complete contour predictions. Thank you for your attention. If you are interested in our work, please refer to our conference paper for more information.